Welcome back to Mrs. Ogram's Maths. This video is going to take you through a practice paper for Achievement Standard 91578, which is the integration paper for Level 3 Calculus. Question 1, we're asked to integrate 10 sec squared 5x. So sec squared integrates to tan x, that's on your formula sheet, so that would be tan of 5x. And then we would divide by the derivative of what was on the inside there, so we're dividing by the 5. So 10 divided by 5 gives us 2. Part B, we've got another fairly straightforward integration. I'm just going to rewrite that as a fractional power first to make this easier to see. So x to the third, we increase the power by 1, that gives us x to the 4 over 3, divide by the new power, so that is 3 over 4. And if we integrate 1 over x plus 1, that is the natural log of x plus 1, like this, and the derivative of the inside of that bracket was just 1 from the x plus 1, so we don't need to do anything else there. Right, for part C, we are looking at kinematics. We've got some information about the acceleration. So the acceleration function is here, and we want to work out what was the velocity. We've been given the initial velocity of 5 meters per second there. And we're going to work out the velocity of the object at 6 seconds. So to get velocity from acceleration, we integrate. So v of t is equal to the integral of 2t over 1 plus t squared. Now recognize here that the top of this fraction here is the derivative of the bottom, which means that that is going to be the natural log of the bottom. Okay, then we know that when t is 0, so the initial time, the velocity will be 5. That will help us to work out c. So v of 0 equals ln of 1 plus 0 squared plus c, and we know that that is equal to 5. Now ln 1 is 0, so therefore c equals 5, and our velocity function is ln of 1 plus t squared plus 5. So when t equals 6, if we put 6 into our velocity equation, we've got ln of 1 plus 6 squared plus 5. If you pop that into your calculator, you get 8.61, and we need to think about what units that would be measured in. So we had the acceleration was meters per second squared, therefore the velocity will be meters per second. For part D, we want to find the shaded area just here in the middle of those two sections there. So that's we've got a tangent that's being drawn to this curve here. So what I'm going to do is find the area under the curve up to where that tangent crosses, and then take away the area of the triangle that's underneath it. And we're told that that tangent happens at 1e, so it will happen at this point here where x is equal to 1, and the y value is e, so that length there is e. Okay, so now we want to integrate the function. So e to the x between 0 and 1 will give us that area under the curve. Now if we integrate e to the x, we simply get e to the x. So then we get e to the 1 minus e to the 0, or e minus 1. And then the area of the triangle will be half times the base times the height. So that is half e. So then the shaded area is equal to e minus 1, take away that triangle, and that comes to 0.359. Okay, now part E of this question was actually really quite a tricky integration to do. So y will be the integral of this function here, 1 over x ln x, but there's no easy way to do that. What you can recognize though is that this is the same as 1 over x times 1 over ln x, which you can imagine as being 1 over x over ln x, and then you've got the top is the derivative of the bottom, which then means that you do the natural log of the bottom. So y would be equal to the natural log of what's on the bottom, which is log of x, and then plus c. Now you can check this, you can differentiate that again if you wanted to, so you can do the chain rule on it. You would get back to 1 over x times 1 over ln x, which was our original function there. It's quite a tricky one to recognize. Okay, so now we've got that y equals this. We can use that if y equals ln 2 when x is equal to 2 up here, so we can work out what c is. So this is equal to ln 2 when x is equal to e to the 2. Well, natural log and e, they cancel each other out, so that'll be ln 2 plus c. And then ln 2 cancels with ln 2, so therefore c is equal to 0, and y is just ln of x. Alright, for question 2a, you reach for your formula sheet and you plug it into the Simpson's rule formula. So that is a third multiplied by the height, for which you can either do the 2 minus 0 and divide it by how many spaces you have in between, or you can just simply look and see these are going up in 0.25, so that's your height, 0.25. And then we have y0 plus the first y plus the last y here, and then add 4 times all of the odd y's. Now remember, this is y0, it starts at y0, not y1, so this is y1. And then we have y3, y5, and so on. So we've got 2.8, 2.4, 1.8, and 1.5. And then add on 2 times the even ones. So 2.5, 2, and 1.4. And that comes to 4.21. Part B, we need to integrate 7x minus 2 to the 4. So it's reverse chain rule. So 7x minus 2, raise the power by 1, we get a 5. And then we need to divide by the new power. So it'd be divided by 5. So if we put a fifth at the front, but we also divide through by the derivative of the inside, which is 7. So if we divide by 5 and we divide by 7, we'll end up dividing by 35. Part C, we need to integrate to get y, but we've got the x and the y's mixed together on the right hand side, so we need to separate them first. So if we bring the root y dy to the left, and we'll take the dx to the right, and I'm going to change that square root into a power to the half, and then we can integrate both sides. So y to the power of a half becomes y to the 3 over 2 times 2 over 3, and 2x becomes x squared, and then plus c. Then we can use y equals 1 when x equals 1, so pop that in here and we'll get 2/3 is equal to 1 plus c. So c is equal to minus 1/3, and we get 2 over 3 y to the 3 over 2 is equal to x squared minus 1/3. Finally, we want to work out that value of y when x is equal to 2. So pop our 2 in when x equals 2. We've got 2/3 y to the 3 over 2 is equal to 4 minus 1/3, and then work that through. And that comes to the decimal 3.116. We've got a kinematics question for part D, which just takes a little bit to wrap your head around what you're being told here. So we are first of all told the balloon is rising at a rate of this many meters per second. So that's the speed that it's going up, or the velocity. So the velocity of our balloon is equal to 3 minus the cubed root of t. It's going to burst when the velocity becomes 0. So if we set that equal to 0, that's going to give us something in a moment. And we want to know how high does the balloon go. Oh, let me just fix that up. So how high does the balloon rise before it bursts? So that one we're looking for a distance. So to get distance from velocity, we will need to integrate. Now let's find out when that happens first. So we can solve this bit here of when the velocity equals 0 to solve for t. So we will have that the cubed root of t is equal to 3. So t is equal to 27. So the balloon will burst at 27 seconds. Now if we integrate 3 minus the cubed root of t, then we will get the distance function. And if we want to know how far it's gone in that time, we're going from the time of 0 to 27, we can put those limits on like so. So 3 integrates to 3t. The cubed root of t, that's t to the third. So this becomes minus t to the 4 over 3 divided by 4 over 3. So 0 to 27. So if we substitute in those limits, we've got 3 times 27 minus 3, or 3/4 of 27 to the 4 over 3. If we put 0 in there, it's going to come out to 0 on both of those terms. So this will give us our answer of 20.25, and we're measuring in meters. Part E on this question, most people actually struggled to understand what it was telling you in the information here and then went off in the wrong direction. So let's just take a minute to pick this apart. We've got the curve y equals e to the x, so that's the blue one on both of these diagrams, and the curve y equals k x to the 0.5 plus 1. Now I emphasize that k because that's the thing that gets changed on each of these different curves. So we've got the first one is when k is 4, the second one is when k is 5. And it's just giving you an example of what that curve could look like. Now find the area of the space between the curves when the x-coordinates of the points of intersection are 0 and 2. So if you look here, we've got a x-coordinate of 1.866 and one of 2 there. We need to find out what value of k would give that value of the x-coordinate to be 2. It's always going to intercept at the 0 down here, but we need to find out what function we can put in, what value we can give to k so that that x-coordinate of intercept comes out as 2. So if I draw a little picture of what I'm talking about, that might help. So we've got our graph here, we've got the original e to the x, and then we have some other function like this, y equals k, it was to x to the 0.5 plus 1. And we need this intercept just here to come down at 2. So if we were looking for the intercepts, we would set these two things to be equal to each other and solve for x. But since we know that x has to be 2, we can replace that with a 2 in there and use that to solve for k. I'm just going to fix up a small error I made there. That plus 1 is outside of the power. So that's a plus 1 here. So k will be equal to e to the 2 minus 1 divided by 2 to the half. And now we can go on to find the area here between these two curves when k has that value. So that means we're going to integrate between 0 and 2, and we'll take the top one, which is y equals k x to 0.5 plus 1, but k is this value here. So e to the 2 minus 1 over 2.5. Now that is just a constant, so don't be afraid of it. And then it's x to the 0.5 plus 1. And then subtract the curve that's underneath it, which is e to the x. So it's not a very pretty looking integration, but it's not too difficult to do. This e squared minus 1 over 2 to the half, let's just leave that there as a constant. We'll do x, raise the power by 1 and divide by the new power. So just leave that like that. It's probably easier to work it out like that. 1 becomes x, and e to the x is just e to the x, and we will put in the values of 0 and 2. Now when you put 2 into all of that, you get 3.12. Actually, no, I rounded wrong. It's 3.13. And then when you put 0 in, well, most of it goes away except for this e to the 0 at the end, so it's minus e to the 0. Anything to the power of 0 is 1, so that's a minus 1, and we get 4.13. Question 3 starts us off with a straightforward integration, which I'm just going to put into fractional, or rather negative powers first. E to the half x like this, because I find that much easier to think about what's going on. So raise the power by 1, we get x to the minus 4. If we divide by that minus 4, we will have a minus 1 at the front. E to the half x stays as e to the half x, but we divide through by that half, so that will be a 2 at the front there, and then plus c. For part B, we want the area between the graph, the x-axis, and the line x equals pi by 4 and x equals 3. So let's just give a little sketch of that first, because we want to check that none of those areas are going to cross over the x-axis. So sine of 2x means that instead of going through the x-axis at pi and 2 pi like sine of x would, it'll go through at pi by 2 and pi here. Okay, so pi by 3 and pi by 4, they're both on this side of the graph, so we're good to go, just integrate straight between them. So pi by 3 up to pi by 4 of sine 2x. And you get minus a half cos 2x. And put in pi by 3 up to pi by 4. And I just realised I made a silly mistake and wrote these the wrong way round, because a quarter is smaller than a third. So when you do that subtraction, it should be this way round, and your area comes to a quarter. For part C, we need to find the value of k that makes this thing true. So if we were to integrate from 0 to k, 4x of x squared plus 2 dx, then first of all recognise the top of that is the derivative of the bottom, or rather a multiple of it. So therefore we can do ln of x squared plus 2. It's not directly that thing, it's 2 times of that thing. So, because if you differentiated ln of x squared plus 2, you'd times it by the 2x, and we want 4x on the top, so it's got to be twice as big. And that will run between 0 and k, and then we can set it equal to 2 ln 4. So 2 ln of k squared plus 2 minus 2 ln of 0 plus 2 will be equal to 2 ln 4. So we can divide everything through by 2, and we get ln k squared plus 2 minus ln 2 is equal to ln 4. So ln k squared plus 2 will be equal to ln 4 plus ln 2. Now if you add together logs, you can multiply their inside parts. So that becomes ln of 8, that's just your log laws. So k squared plus 2 must be equal to 8. K squared is then equal to 6, so k is plus or minus the square root of 6. But since our integration at the top put k above 0, we can assume that k is that positive square root of 6, and we just can write it like this. Part D uses Newton's law of cooling, which is that the cooling of an object is proportional to the temperature difference between the object and its surroundings, if that difference isn't too large. We've got a piece of meat at room temperature, which is 18 degrees C, placed in a fridge, which is 2 degrees C. After half an hour, the meat has cooled to 6. We want to then work out the temperature of the meat after another half an hour. Let's start by setting out some things like little t is going to be the time, and the capital T will be the temperature at that time. So we're looking at the rate of change of that temperature over time. Now we're told that that rate is proportional to the difference between the temperature of the thing and its surroundings. So it's proportional to its temperature, and the surroundings is the fridge temperature, which is 2. So the difference between them would be T minus 2. Now if something is proportional, we can write it as equal to a constant times that thing. So we've managed to link together those variables. What we're aiming for is to be able to work out the temperature after another half an hour. So we're aiming for something where we can write a function of T equals and plug it in and work out what that temperature would be. So to get that, we'll need to separate these variables. So we will need to bring anything that's capital T to one side and little t to the other. So we can take 1 over T minus 2 to the left and leave the k there and put the little t on the right and integrate both sides of that function. So 1 over capital T minus 2 will give us the natural log of T minus 2, and k would just become kt plus some constant. So then T minus 2 would be e to the kt plus c. Now this is the same as e to the kt times e to the c, which again in itself is a constant, which we would usually just write as a separate constant like this. So then t equals a e to the kt plus 2, and we've got our function t equals something, but we've got an unknown a in there, so we need to try and work that out. For that we use the starting temperature. So when T was equal to 0, the starting temperature of the meat was equal to 18. So 18 equals a e to the 0 plus 2. So a equals 16 and t is equal to 16 e to the kt plus 2. Now we've still got a constant in there of k, so we use the other bit of information we were given, which is after half an hour the meat has cooled to 6. So if we're measuring it in hours, when t is 0.5 hours, t is equal to 6. So 6 equals 16 e to the k times 0.5 plus 2. So 16 e to the 0.5k is equal to 4. If we divide through both sides by 4, we get this. So e to the 0.5k is equal to a quarter. Take ln of both sides, we get 0.45k is equal to ln of a quarter. So k is equal to 2 ln of a quarter. Finally, the last bit, work out after another half an hour, so that will be when t equals 1. Then the temperature will be equal to 16 e to the 2 ln of a quarter times by 1 plus 2. Pop that into your calculator and you will get exactly 3 degrees C. Alright, the last one. We've got dy by dt is equal to this function over here, so we need to separate the variables. So if we bring the y's to the left hand side, we get 1 over y plus 2 dy is equal to sine squared t dt, and then we want to integrate each of those. So on the left we get ln of y plus 2. On the right we need to do something with that sine squared. First of all, we can't integrate it as it is. But on your formula sheet you have 1 minus 2 sine squared. I'm going to say t. On the formula sheet it has an a, but that's equal to cos of 2t. So if we rearrange that, we will get that 1 minus cos t is equal to 2 sine squared t. So therefore sine squared t is equal to 1 minus cos over 2. So pop that back into here, and we are now trying to integrate 1 minus cos, oh, whoops, I missed the 2t over here, so missed out the 2 when I moved it over. And then that's over 2 with respect to t. And then that's probably actually easier to think of as 2 separate things. So it'd be 1 over 2 and this over 2. We can just separate them out. So the half becomes t over 2. Cos integrates to sine, so this is minus sine of 2t, and then we'd have to divide it by the 2 that's in the 2t, and also it's got a dividing by 2, so altogether we're dividing by 4 plus c. Next is to work out what that plus c is by using that when t is 0, y is 0. So we get ln 2 is equal to 0 minus 0 plus c, so therefore c is equal to ln 2. So back to our equation, we have t over 2 minus sine 2t over 4 plus ln 2. And let's see when we want to work that out. We want the exact value of y when t is pi by 4. Now note its exact value. So we should be giving the exact answer, although the mark scheme did actually accept the decimal here. So let's go back down here. So substituting in pi by 4, we get pi by 8 minus 1/4, because sine of 2 lots of pi by 4 is going to be 1, and plus ln 2. So y plus 2 will be equal to e to the pi by 8 plus, minus 1/4 plus ln 2. So y will be all of that minus 2. And the decimal answer did actually get accepted, I think, because that was just so untidy, that one. And that came to 307.307.